Okay, glad to be here. So not to be outdone by Jason or Kevin, this is a talk in 3 parts, and I have way too many slides. So this was originally conceived as a poster to showcase the work of our NASA Astrobiology Institute team at JPL, the NAI Icy Worlds. So the first part will be to quickly highlight what I would have shown in a poster by just going through some slides showcasing the different parts of our team, now teams, as you'll see. So followed by what's crafted as a response to yesterday and today's discussion, which I guess will be the bulk of it. And if I have time, I'll get to some fun thermodynamics. That's a real thing. This is the cover of our proposal. My partner likes to point out that these proposals always turn out looking like the cover of a sci-fi novel. But I think this nicely summarizes what we're trying to do in this big project. We have a lot of different team members, and it's not meant to be an exclusive club. We collaborate with a lot of people who are not part of the original proposal. But the idea is to look at the possible origin of life in alkaline systems and also high temperature systems in icy ocean worlds. And then Jason Goodman's part of our team. Think about the transport of materials vertically through the ocean into the ice, what's happening in the ice, and then how to detect those things on the surface. The part 2 of this, the sequel to that novel, also uses the word and beyond, the phrase and beyond. Is the recently selected Titan project. I'm happy to be a part of that as well. So I'm leading aspects of each of these projects, and that allows me to couple a lot of fun thermodynamics into looking at the interiors of icy ocean worlds. Okay, so our Icy Worlds team has 4 main parts. Mike Russell is a member of our team at JPL. He's known as a proponent for an origin of life in alkaline hydrothermal systems. He continues to think about how that might have happened on Earth. Most recently, he's gotten excited about the role of nitrogen and the role of methane as an input rather than something that's produced by these systems. And he's also, by virtue of being at JPL and collaborating with the lander team, thought about what life in Europa might look like. And I like this insight that because the highest energy gradient might be right at the ice-ocean interface, that might be the best place to accumulate life. Maybe Kevin can speak about that paper if that comes up in discussion. So another part of our team, big component of our 4-part team, is work led by Laurie Bard, which is sort of the experimental complement to what Mike is doing. So largely, Laurie has been looking at laboratory chemical gardens as ways of testing different aspects of hydrothermal chemistry. So Mike is interested in green rust. Laurie is interested in green rust. She's been looking at nitrogen and phosphorus, interacting with those. A couple of highlights from that work is that they can create ammonia by including nitrogen in these systems, and they find that adding amino acids to their systems causes increased sequestration of phosphorus into these chemical gardens that they create in the lab. Green rust is a ferrous double layer oxyhydroxide that forms these layers that are canted. And that is, they're not fully planar, and they can shuttle molecules across a strong redox gradient. We should talk in more detail after this, though. Is that a satisfactory answer? Okay, so the part that I'm leading, part 3, looks at, again, the tracking of materials from the seafloor outward. So we have a lot of different collaborators. Again, Jason's one of them. And so we ask a lot of different questions about the role of orbital variation, fluid transport, the role of high pressure ice. So I won't dwell on that because a lot of the material that I'll show in a minute has to do with that. So here's sort of how we shuttle from investigation 1 through. So the idea is that ideas from investigation 1 feed into the experiments. We have a whole set of different things we can look at in investigation 3. And then those lead to predictions that can be tested in the lab in terms of observable signatures. And so just getting to that part 4, Rob Hodis and Paul Johnson are the main leads for that. Matusha Krohn and Tuan Vu have been doing a lot of work as well. So a neat thing, and here demonstrated for series, with a nice connection to the previous talk, is the idea that things that are deposited on the surface are dependent on the way in which they're deposited. That is, whether you flash freeze them or slowly freeze them. So here they've taken an initial solution, either equal molar constituents or biased with more ammonia, ammonium, or sodium. And in each scenario, you get different resulting output, so things that you might see on the surface. So the context is important. Okay, that was part one. So let me get into some insights about icy ocean worlds that I hope we can discuss for the remainder of the meeting. I wanted to respond about this idea of pores driven by the thermal expansion and anisotropy. So this is a figure from a recent paper. Kevin was involved with that. He highlighted some of the results of that yesterday. I like this figure for summarizing a lot of information about icy ocean worlds and known ocean worlds, shown with unique colors here. So here's pressure on the vertical axis increasing downward to the base of Ganymede's ocean. And I'm starting with each object at where its rock-water interface occurs on the basis of these simple two-layer models. And this schematic is showing the light-colored region as the region where porosity can occur. And that region is calculated as the region of seafloor that is above the thermal cracking front in pressure and temperature. So you can imagine calculating this for a given world just by computing how much depth this P and T region corresponds to. And so we did that in this 2017 paper, 2016 paper, also an earlier work, 2007, where I coined the term small ocean planets at the time when Pluto had been demoted. I like that as a solution to thinking about icy ocean worlds. Anything spherical is with an ocean is a small ocean planet or a SOP. Okay, so getting back to something, referring back to something that Kevin summarized yesterday, this is a different way of looking at the figure that he showed. So here I'm showing redox flux, moles per year, and this is as a function of tidal heating in Europa's seafloor. You can imagine doing this exercise for another world as well. Also, roughly speaking, the ice shell thickness will vary based on this as well. So if you have less heating in the base, more heating might happen in the ice shell. So above about 10 kilometers, you can presume that the ice becomes more dissipative tidally, and there's less high temperature hydrothermal activity happening in the seafloor. Okay, so I'm going to show different molar fluxes. Here's Earth's net H2. Kevin showed this yesterday. This is based on inventories Barbara Sherwood-Lawler and others have done. Here's the O2 flux to Europa's ocean. This is very analogous to the work that Christine Ray just shared for Enceladus, and this is largely work that Kevin did in the aughts, but also Rick Greenberg responded and supposed that the amount of O2 is actually a lot larger. So I'm covering a really broad range here. You can think of this as the absolute minimum, potentially, and the absolute maximum. You can see that's still lower than Earth's net H2 and much less than Earth's net O2. Kevin showed figures that were comparable to Earth because the figure that he showed was on a per unit area basis. That's important to keep in mind. I've parameterized the H2 from high temperature hydrothermal activity using a flow model. Basically, hydrothermal flow helps to get the heat out. And so you can figure what is the number of hydrothermal systems on Europa and what is the corresponding amount of hydrothermal activity corresponding to the total heat at the seafloor. And that's in the paper. Okay, so the other thing you can do is compute what is the amount of H2 from crustal serpentinization if you have a basis for the depth of the fractured region from thermal expansion and anisotropy. And so that depth is greater if you have less heating in the seafloor. And actually what's more important is that as the body cools, you're fracturing deeper and deeper through time. And so this rate is actually only the serpentinization of that micrometer or so of material that's being exposed on an annual basis. And you can see, interestingly, that for the parameters that we chose, the amount of H2 from serpentinization is comparable to that from hydrothermal activity. So those are neat. That's a neat way to think of things. You could imagine doing this for Enceladus. Here's actually an order of magnitude. Well, this is in the neighborhood that Christine presented. What's important to note is that the ocean thicknesses for Europa and Enceladus are probably much different. I reckon that 10 kilometers is a good number for Enceladus's ocean. 50 is probably the upper limit. And so you even though the fluxes are different, the per volume amount per year is comparable. Well, still a little bit less for Enceladus. So it's also interesting to think about. Okay, so another thing that I want to talk about, switching gears a little bit, we mentioned this earlier. We can actually, these are the inputs to the material that Paul presented earlier. So we can actually compute what is the radial structure of a given ocean world based on the known radius, known density, and the moment of inertia, which is roughly speaking the gravitational parameter that tells you how much the density is concentrated toward the interior. So this comes from babysitting a spacecraft. Okay, and what's important here with Planet Profile, the software that I developed, is that I'm using thermodynamic properties, the best available thermodynamic properties for the ice, for the ocean, including the effect of salinity, and also modeling the properties of the rock and a core if there is one. So I can tell you the details about that offline. I don't have slides for those details. But in broad strokes, it accounts for the influence of ocean composition, like I said. So we can use this in the future to do water-rock interaction modeling. And I'm discussing that with Mohit Melwani Daswani, who's in the audience. Okay, and again, useful for geophysical inversion stuff. So this paper that we published goes through many ways you might apply these kinds of calculations. But in summary, what we're doing is we have a model for the temperature profile in the ice, and the boundary condition is simply the bottom temperature of the ice. And so you arrive at an analytical representation of the temperature profile if you assume that it's conductive. You can later assess whether it's actually undergoing solid state convection. We do that. Nice thing about doing it this way is that the corresponding heat flux independently comes out, is only dependent on your coefficient of thermal conductivity. So then the ocean we assume is strongly convecting. I think Jason argued pretty effectively as to why it should be the case. So this is how the adiabat works. The temperature of the ocean increases with depth as the ocean compresses, similar to our atmosphere. And so that's dependent on the thermal expansivity, the temperature, the density, and the heat capacity. These are all thermodynamic properties that we can measure. Okay, so this is the paper that we published on that. And so we test where ices occur. So this is what Jason was getting at earlier in a lot more detail. Let me walk through this a little bit because this is kind of neat. So here's from our models. This is an output for Titan. Big picture, based on our assumptions, you have a H2O layer that's about 470 kilometers thick. And what I'm showing here is density versus pressure. So here we start at 0 pressure at the surface. We go through the ice heats up, and so it becomes less dense as you go into the interior. For the cold model for Titan, the pressure at the base of the ice is quite high, 2,000 atmospheres. So the temperatures simply correspond to different assumptions about the bottom temperature. So the magenta is a warmer ocean. Once we reach the ocean transition, we follow the adiabat. And so this is the adiabat for a pure water ocean. Here's the adiabat for 10 weight % magnesium sulfate ocean. These dashed lines, these with the same line marker style, are simply references for what you would have if you had a much more saline ocean or a much less saline ocean. And so we cruise along that until we reach the stability field for a given ice based on our thermodynamics. And so here we transition to ice 5 for this cold case, and later on we transition to ice 6. And the circles simply show what is the predicted seafloor depth. And you can see that actually depends on the salinity and the temperature. So different models have different depths. And we can translate that to depth, and here as a function of temperature. So same data. You're in the ice 1. You transition to the ocean. So here I'm showing the ocean adiabats. Sorry, these are the ocean adiabats. This is the convective ice shell. You can see that the ocean is warming up quite a lot as you move downward. For the warmest ocean, for the pure water case, for Titan, you can actually get rid of the high pressure ice altogether, even for a pure water case. I find that pretty interesting. For the cold cases, you still get quite a lot of high pressure ice, something on the order of hundreds of kilometers. And so our thermodynamic data are based on sound speed, so we can predict what is the sound speed profile in the ocean for a given composition. That's 20 minutes left? Great. Okay. So I can do the same thing for Callisto, the less talked about ocean world. That's actually pretty interesting. Our current value per moment of inertia of Callisto puts it in the stability field for ice 5 and not ice 6. So that's kind of interesting. Also because Callisto is probably a relict ocean world with this nearly frozen out, you might expect to have a high salinity ocean. And so for high salinity ocean, around 10 weight % MgSO4, you can get ice 3. However, ice 3 is less dense than the ocean, and so it should float. but it can't float to the top because it'll melt once it gets close to the top of the ocean. So you can imagine these upward snows of ice 3 forming. Okay, and this sort of behavior is observed in the lab. Our postdoc, Baptiste Journeau, for his thesis, looked at high-pressure ices in a diamond anvil cell. This is a sodium chloride solution. For high enough salinity of NaCl, the ice floats in the diamond anvil cell. Okay, Christophe Sautin is working with us. This is the paper that Jason mentioned by Clara Kalasova. Indeed, for different thicknesses of the high-pressure ice layer, you either have a heat pipe-like mechanism. Red is showing the occurrence of melt. So here, melt is helping move fluids up. You have this interesting few kilometers of H2O at the base. If the ice is much thicker, you get more of a solid-state convection-like mode where the fluids are helping and also driving things away from the adiabat. And if you're much thicker, like 400 kilometers, that scenario sort of goes away, and you have much less fluid at the base. None of this accounts yet for the role of salt, and so we're working toward that. This is from a paper by Baptiste that just came out that's using his experimental data to examine what could happen as salts are included. First insight is that salts are strongly included within the ice matrix in high-pressure ices by a factor of 10 over what's included in ice 1. And they actually change the density of the ice, and so they do that in a way that in ice 7, which is applicable to exoplanets, the salt decreases the density of the ice at low pressure, and at higher pressure increases the density. So that would affect the dynamics of the ice. I'll just stop at this slide and the following slide, which are speculating on the ability to determine the nature of the rock layer if we landed on Europa or another ocean world. If we had a seismometer to intercept a seismic source in the ice, a portion of that seismic energy would propagate through the ocean, through the mantle, to the ice shell. Yet another portion of that seismic signal could actually be a surface wave, so-called Schulte wave, trapped in a low-density layer, sediment or serpentinized material that we might be able to pick up if we have long enough time at the surface. I'll just stop there. Thanks. And if you want...
Thank you, Steve, for a very entertaining talk. Questions? Yeah.
Thanks. Interesting talk, Steve. I'm just wondering, I haven't really looked into it. What is the reasoning behind magnesium sulfate? Is that minimum eutectic or versus maybe just an NaCl?
Yeah, I have some slides about that. I can get to them. Okay, so here's the way I think about it, and this is from work that Misha Zolotov did. This is the log molar dissolved stuff as a function of pH, basically log H2 fugacity. As the pH lowers, you can have much more dissolved magnesium and sulfate. If those things are available, you can have a scenario where magnesium and sulfate are more abundant than the sodium and chloride. The reason I've studied magnesium sulfate in the past is historic, that people saw magnesium sulfate at the surface and thought that was what was in the ocean. But yeah, it's a complicated story.